Welcome to Ask and Learn.
A player bounces a basketball on the floor, compressing it to 80% of its volume. The air, essentially nitrogen gas, inside the ball is originally at 20 degrees Celsius in 2 atmospheres. The ball's inner diameter is 23.9 centimeters. A, what temperature does the air in the ball reach at its maximum compression? Assume the compression is adiabatic and treat the gas as ideal. And B, how much does the internal energy of the air change between the ball's original state and the maximum compression? So let's start this problem out by recording what's given to us in the problem. So we know that, first of all, it's air. So we can write down the heat capacity of air, which should be found in the chapter, and it's 29.76 joules per mole Kelvin. And the corresponding gamma, which is the ratio of the heat capacities for constant pressure and volume, and that's 1.4. And finally, we want to get the initial temperature, or not finally, but next we want to get the initial temperature. It's 20 degrees C, so we want to convert that to Kelvin for our calculations. So we just need to add 273. So then that gives to add 273.15 to that. So that's 293.15 Kelvin. And we want the initial pressure. So P initial is equal to 2 atmospheres. And then if you convert that to pascals by multiplying by the conversion factor, then you get 2.026 times 10 to the 5 pascals. So we want it in SI units. And then okay. So to relate the variables, we need to acknowledge that it's adiabatic compression. And so for adiabatic compression, you get a certain set of formulas that are true, always true about the temperature, volume, and then the pressure and volume. So we're going to use the one for temperature and volume to get the final temperature. So the formula you want to use is T final equals T initial times V1 divided by V2, V initial divided by V final. And we want to take that all to the power of gamma minus 1. So if you plug in numbers to that, you're plugging in 273.15. And then V initial is just going to be V initial. And then V final we know is 0.8 times V initial. And we want to set that to the power of 1.4 minus 1. And then if you do that, the VI's cancel, and you're just left with 1 over 0.8 to the 0.4 power. Times 273.15. And if you put that into a calculator, then you should get 320.5 Kelvin. And then if you convert that back to Celsius by subtracting 273.15, then you get 47.4 degrees Celsius. Great. So for part B, it asks for the final volume. And let's see. Oh, excuse me. It asks for the change in internal energy. So to get the change in internal energy, generally the formula is U is NCV multiplied by the change in temperature. So this is going to be a delta U, and then that's going to be a delta temperature. And let's see. So looking at this equation, it's clear that we have CV and we have delta T from part A, but we don't have N, so we need to find N first. So I'm going to underline that, and then maybe I'll write in red. So to find N, you want to use the ideal gas law, PV equals nRT, and if you rearrange that and divide the nRT by RT, both sides by RT, then you get N is equal to PV. And so we know the initial pressure. We have all the quantities to calculate this. So the initial pressure is 2.026 times 10 to the 5 pascals. The initial volume, I'm just going to use all initial, although we could use final if we wanted to, because the number should stay constant. Okay, so now we need the initial volume. The initial volume is the volume of a sphere, so it's 4/3 pi times the radius cubed. Oh, and I didn't record the radius up here, so I'm going to go ahead and do that, and then maybe kind of draw a line to make it less sloppy. Oops. Okay, we know the diameter is equal to 23.9 centimeters. And then actually, oops. I'm going to go ahead and erase radius and actually put the radius in since I'm doing numbers here. So the radius is going to be half the diameter, and we also need to convert it to SI units to make sure we get moles for our units of numbers. So make a little. So converting 23.9 centimeters to meters is just 0.239 because there's 100. It just becomes 2.239 meters because there's 100 centimeters per meter. And you want to divide that by 2 to get the radius. So the formula for the volume of a sphere is 4/3 pi times radius cubed. So we have to divide the diameter by 2 to get to the radius. Great. And then now this whole thing is over R times T initial. And R is equal to, let's see, 8.314 joules per mole Kelvin. And the initial temperature, like we said, was 293.15. Okay, great. So if you put this whole expression into a calculator, then you obtain that there was 0.594 moles of gas in the basketball, which is a reasonable number because moles are usually on the order of 1. So I'm going to go to the next page to keep going with this problem. So we said change in U is equal to N CV delta T. And now that we have N, we're ready to plug in to get the change in U. And I think does it ask for the final U or just the change in U? It just asks for the change. Okay, great. So N, we said from part 1 is 0.594. And then CV, we said, was 20. 1 second. Okay, let me look up the heat capacity for air. I just want to double check. I have a discrepancy in my notes. So I'm looking on the book, and on table 9.1, it has the heat capacity as 20.76. So let me see if that's what I actually had in my first sheet. Okay, I had 29.76, so I need to correct that error. Oops. Okay, great. Now we have 20.76 as the heat capacity. So now I'll move on back to my other table to compute that. So 0.5954 moles times 20.76 joules per mole Kelvin. And that's multiplied by the change in temperature, which we know from part A and the given information that it's going to be 320.5 minus 293.15 kelvins. And if you take all of that and you plug it into a calculator, then you get 345 joules. And I'll go ahead and box that.